Hello everyone. In previous class, we discussed about the feedback amplifier and the classification of feedback amplifier like positive feedback amplifier and negative feedback amplifier. In this lecture, we will study about what is oscillator, comparison and difference between the feedback amplifier and oscillator. Next is a classification of oscillators. After this, we will move on sinusoidal oscillators. Next is RC oscillators. And the reference of this presentation. So, in this lecture, we will cover or learn all these topics one by one. Let's start with topic 1, oscillator introduction. इसमें हम देखेंगे कि oscillator circuit actually होता क्या है और why we require oscillator circuit, as well as the comparison and difference between oscillator and amplifier circuit. चलिए स्टार्ट करते हैं. Oscillator. An oscillator generates output without any AC input signals. An electronic oscillator is a circuit which converts DC energy into AC at a very high frequency. An amplifier with a positive feedback can be understood as an oscillator. तो oscillator एक ऐसी डिवाइस है जो कि जनरेट करता है आउटपुट विदाउट एसी इनपुट के, और हम कह सकते हैं कि ऑसिलेटर एक ऐसी इलेक्ट्रॉनिक्स डिवाइस है जो कि कन्वर्ट करता है डीसी एनर्जी को एसी एनर्जी. नेक्स्ट इज एम्पलीफायर वर्सेस ऑसिलेटर. An amplifier increases the signal strength of the input signal applied, or we can say that the amplifier is a circuit which is boost the power level of the input signal, whereas an oscillator generates a signal without that input signal, but it requires DC for its operation. This is the main difference between the amplifier and the oscillator. Take a look at the following illustration. It is clearly show how an amplifier takes energy from DC power source and convert into AC energy at a signal frequency. An oscillator produces an oscillating AC signal on its own. So this is the diagram. First one is called the diagram of amplifier. We need the AC input. In case of oscillator circuit, we do not need the input signal, we need only the DC power input supply. The frequency waveform and the magnitude of AC power generated by an amplifier is controlled by the AC signal voltage applied at the input, whereas those for an oscillator are controlled by the component in the circuit itself, which means no external controlling voltage is required. So next we compare alternator versus oscillator. Alternator is called the synchronous generator. An alternator is a mechanical, or we can say that the electrical device that produce sinusoidal wave without any input. This AC generating machine is used to generate frequencies up to 1000 Hz. The output frequency depends on the number of poles and the speed of rotation of the armature. सिंपल हम बोलें तो जो अल्टरनेटर होता है, सिंक्रोनस जनरेटर को हम अल्टरनेटर बोलते हैं, उसको हमें बस प्राइम मूवर के थ्रू उसके रोटर को घुमाना होता है और वी गेट दी AC इनपुट. The following points highlights the difference between an alternator and the oscillator. An alternator converts mechanical energy into electrical energy, whereas the oscillator converts DC into AC energy. An oscillator can produce higher frequency of several megahertz, whereas the alternator cannot. Means alternator जो है वो इतनी मेगाहर्ट्ज में फ्रीक्वेंसी को प्रोड्यूस नहीं कर सकता, बट ऑसिलेटर मेगाहर्ट्ज में फ्रीक्वेंसी को प्रोड्यूस और जनरेट कर सकता है. An alternator has rotating parts, whereas electronic oscillator doesn't. It means alternator जो होता है वो एक rotating electrical device है जिसमें कि एक रोटेटिंग पार्ट होता है जिसको हम रोटर बोलते हैं, बट ऑसिलेटर सर्किट में कोई भी रोटेटिंग पार्ट नहीं होता, बिकॉज ऑसिलेटर इज अ इलेक्ट्रॉनिक सर्किट और इलेक्ट्रॉनिक डिवाइस. It is easy to change the frequency of oscillation in oscillator than in alternator. तो अल्टरनेटर के कंपैरिजन में ऑसिलेटर में फ्रीक्वेंसी को चेंज करना बहुत ही आसान होता है. Oscillators can also be considered as opposite to rectifier that convert AC to DC, as these convert DC to AC. So the next topic is classification of oscillators. Oscillators are broadly classified into two categories. First one is sinusoidal oscillator and second is a non-sinusoidal oscillators. So electrical oscillator are classified mainly into the following two categories. Number one, sinusoidal oscillators and non-sinusoidal oscillators. So what is sinusoidal oscillators? The oscillator that produced an output having a sine waveform are called sinusoidal or harmonic oscillators. Means sinusoidal oscillators को हम harmonic oscillators भी बोलते हैं. Such oscillators can provide output at frequencies ranging from 20 Hz to 1 GHz. Second is non-sinusoidal oscillator. The oscillator that produced an output having a square, rectangular, sawtooth waveform are called non-sinusoidal or relaxation oscillator. Such oscillator can provide output at frequencies ranging from 0 Hz to 20 MHz. Next topic is sinusoidal oscillators. Sinusoidal oscillator can be classified, or we can say that can be further classified into the following category. तो अभी हमने देखा कि जो ऑसिलेटर्स होते हैं उनको ब्रॉड क्लासिफिकेशन हम दो कैटेगरी में कर सकते हैं. पहला तो साइनसॉइडल ऑसिलेटर और दूसरा नॉन साइनसॉइडल ऑसिलेटर. ऐसे ऑसिलेटर जिनका आउटपुट वेव फॉर्म में साइनसॉइडल फॉर्म में मिलता है या साइन वेव फॉर्म में मिलता है उसको हम साइनसॉइडल बोलते हैं. और ऐसे ऑसिलेटर जिनका आउटपुट वेव फॉर्म हमें साइनसॉइडल वेव या साइन वेव के फॉर्म में नहीं मिलता, किसी दूसरे वेव फॉर्म में मिलता है, उसको हम नॉन साइनसॉइडल ऑसिलेटर बोलते हैं. तो अब हम साइनसॉइडल ऑसिलेटर्स पे चलते हैं और इसका डिटेल और क्लासिफिकेशन देखते हैं. सो साइनसॉइडल ऑसिलेटर्स कैन बी क्लासिफाइड इनटू द फॉलोइंग कैटेगरी. नंबर 1, ट्यून सर्किट ऑसिलेटर. सेकेंड, आरसी ऑसिलेटर. नेक्स्ट इज अ क्रिस्टल ऑसिलेटर. और भी हम देखेंगे आगे. तो पहले हम समझते हैं ट्यून सर्किट ऑसिलेटर्स क्या हैं. These oscillators use a tuned circuit consisting of inductor L and capacitor C, and are used to generate high frequency signal. Thus, they are also known as radio frequency or RF oscillators. Such oscillators are Hartley, Colpitts and Clapp's oscillator, etc. Second is the RC oscillators. Their oscillators use a resistor and capacitor and are used to generate low or audio frequency signal. Thus, they are also known as audio frequency AF oscillator. Such oscillators are phase shift and Wien bridge oscillator. तो एग्जाम पॉइंट ऑफ व्यू से हमारा ये फेज शिफ्ट और वीन ब्रिज ऑसिलेटर बहुत इंपॉर्टेंट है, और पहले वाले में हमारा हार्टली ऑसिलेटर जो है वो इंपॉर्टेंट है एग्जाम पॉइंट ऑफ व्यू से. इनको हम डिटेल में पढ़ेंगे नेक्स्ट लेक्चर में. नेक्स्ट इज द क्रिस्टल ऑसिलेटर. सो दीज ऑसिलेटर्स आर क्वार्ट्ज crystals and are used to generate high stabilized output signal with frequency up to 10 MHz. The piezo oscillator is the example of crystal oscillator. ये भी एग्जाम पॉइंट ऑफ व्यू से बहुत इंपॉर्टेंट है. इसको भी हम नेक्स्ट लेक्चर में डिटेल में पढ़ेंगे कि व्हाट इज क्रिस्टल ऑसिलेटर, कैसे काम करता है, सर्किट डायग्राम क्या है, सारी चीजें हम देखेंगे वन बाय वन नेक्स्ट लेक्चर में. Number 4 is negative resistance oscillators. So sinusoidal oscillator are classified into 4 categories. First one is a tuned circuit oscillator, second is a RC oscillator, third is a crystal oscillator, and fourth one is a negative resistance oscillator. These oscillators use negative resistance characteristics of the devices such as tunnel device, a tuned diode. Oscillator is the example of negative resistance oscillator. तो इन जो चारों ऑसिलेटर्स हम पढ़ रहे हैं साइनसॉइडल ऑसिलेटर, उसमें सबसे इंपॉर्टेंट जो है वो हार्टली ऑसिलेटर, फेज शिफ्ट और वीन ब्रिज और क्रिस्टल ऑसिलेटर्स. इनको हम वन बाय वन डिटेल में पढ़ेंगे. नेक्स्ट इज नेचर ऑफ साइनसॉइडल ऑसिलेशंस. The nature of oscillations in a sinusoidal wave are generally of two types. They are damped and undamped oscillation. Normally जो हमारा साइन वेव होता है उसमें जो हमें ऑसिलेशन मिलते हैं, ऑसिलेशन मतलब वेव फॉर्म का ऊपर नीचे होना, उसको हम ऑसिलेशन बोलते हैं. ठीक है. तो ऑसिलेशन जो साइनसॉइडल वेव फॉर्म या साइन वेव फॉर्म में हमें मिलते हैं वो दो टाइप के होते हैं. एक तो डैम्प्ड होता है और दूसरा अनडैम्प्ड होता है. Damped oscillation and undamped oscillation. तो चलिए देखते हैं पहले damped oscillation क्या होते हैं. The electrical oscillation whose amplitude goes on decreasing with time are called as damped oscillation. तो ऐसे oscillation जिनका जो amplitude है वो decreasing होता है टाइम के साथ, उसको हम बोलते हैं damped oscillation. डायग्राम में आप देख पा रहे हैं, देखिए स्टार्टिंग में ज़्यादा एम्पलीट्यूड है, फिर धीरे धीरे कम होते 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 टाइम के रिस्पेक्ट में पूरा कम हो जाता है. तो ऐसे ऑसिलेशन को हम बोलते हैं डैम्प्ड ऑसिलेशन. द फ्रीक्वेंसी ऑफ द डैम्प्ड ऑसिलेशंस मे रिमेन कांस्टेंट डिपेंडिंग अपॉन द सर्किट पैरामीटर्स. तो आप डायग्राम से बहुत ही आसान तरीके से समझ सकते हैं कि डैम्प्ड ऑसिलेशन का मतलब क्या है. ऐसे ऑसिलेशन जिनका एम्पलीट्यूड का मतलब मैं आपको बताता हूँ. यहाँ हम लेजर लाइट का यूज कर लेते हैं. ये है एम्पलीट्यूड, यहाँ पे सबसे ज्यादा है, फिर उससे कम हो रहा है, फिर उससे कम, फिर उससे कम, फिर उससे कम, फिर उससे कम, और यहाँ पे आके ये जीरो हो गया. तो ऐसी टाइप की जो वेव फॉर्म होती है इसको हम बोलते हैं डैम्प्ड ऑसिलेशन, जिसमें एम्पलीट्यूड हमारा टाइम के साथ कम होता जाता है. ठीक है. चलिए सेकेंड देखते हैं. So damped oscillations are generally produced by the oscillatory circuit that produce power loss and doesn't compensate if required. Second is undamped oscillation. So this is the waveform of undamped oscillations. The electrical oscillations whose amplitude remain constant with time are called as undamped oscillation. The frequency of the undamped oscillation remain constant. फ्रीक्वेंसी भी इसकी कांस्टेंट होती है और एम्पलीट्यूड भी कांस्टेंट होता है इन अनडैम्प्ड ऑसिलेशंस का। अब डायग्राम में देख सकते हैं कि यहाँ पे जो एम्पलीट्यूड है वो टाइम के रिस्पेक्ट में कम नहीं हो रहा है, यहाँ पे जो एम्पलीट्यूड है वो कांस्टेंट बना हुआ है और फ्रीक्वेंसी भी कांस्टेंट है। फ्रीक्वेंसी क्या होती है? नंबर ऑफ साइकिल पासिंग थ्रू पर सेकेंड इज कॉल्ड द फ्रीक्वेंसी। तो यहाँ पे फ्रीक्वेंसी भी कांस्टेंट होती है और एम्पलीट्यूड भी कांस्टेंट होता है। तो साइनसॉइडल वेवफॉर्म का जो नेचर होता है उसमें दो टाइप के ऑसिलेशंस होते हैं, पहला डैम्प्ड और दूसरा अनडैम्प्ड। चलिए नेक्स्ट स्लाइड की ओर मूव करते हैं। Undamped oscillation are generally produced by the oscillatory circuit that produced no power loss and follow compensation techniques if any power loss occur. Practical oscillators. In practice, to obtain sustained oscillations at a desired frequency of oscillation, oscillator circuit must satisfy some of the basic requirements such as circuit must have positive feedback, and next, when positive feedback is used in the circuit, the overall circuit gain is given by AF is equal to A1 minus of A into beta. This equation indicates that if A into beta is equal to 1 only, then overall gain becomes infinite. This means there is output without any external input. In reality, to get sustained oscillation at the first time when the circuit is turned on, the loop gain must be slightly greater than 1. This will be ensured that the oscillation builds up in the circuit. However, when a suitable level of the output voltage is reached, the loop gain must decrease automatically to unity. Only the circuit maintains the sustained oscillation, otherwise the circuit operates as overdamped condition. This can be achieved in the circuit either by decreasing amplifier gain A or decreasing the feedback gain beta. The next topic is RC oscillator circuit. It's a type of sinusoidal oscillators. RC oscillators use a combination of an amplifier and an RC feedback network to produce output oscillation due to the phase shift between the stages. In the amplifier tutorial, we saw that a single stage transistor amplifier can produce 180 degree of phase shift between its output and input signal when connected as a common emitter type amplifier, and that is output signal across the collector node depend entirely on the input signal injected into the transistor base terminal. But we can configure transistor stages to operate as oscillators by placing a resistor capacitor RC network around the transistor to provide the required regenerative feedback without the need of a tank circuit. Frequency selective RC coupled amplifier circuits are easy to build and can be made to oscillate at any desired frequency by selecting the appropriate value of resistance and the capacitance. For an RC oscillator to sustain its oscillation indefinitely, sufficient feedback of the correct phase, that is positive in phase feedback, must be provided along with the voltage gain of the single transistor amplifier being used to inject adequate loop gain into the closed loop circuit in order to maintain oscillation, allowing it to oscillate continuously at the selected frequency. So this is the diagram for RC phase shifter. In an RC oscillator circuit, the input is shifted 180 degree through the feedback circuit, returning the signal out of phase, and 180 degree again through the inverting amplifier stage to produce the required positive feedback. This then gives us 180 degree plus 180 is equal to 360 degree of phase shift, which is effectively the same as 0 degree, thereby giving us the required positive feedback. In other words, the total phase shift of the feedback loop should be 0 or any multiple of 360 degree to obtain the same effect. In resistance capacitance oscillators, or simply known as RC oscillator, we can make use of the fact that a phase shift occurs between the input to a RC network and the output from the same network by using interconnected RC element in the feedback branch. For example, RC phase shift network, or we can say that RC phase shifter. The circuit on the left shows a single resistor capacitor network whose output voltage leads the input voltage by some angle less than 90 degree. चूंकि कैपेसिटिव लोड है इसलिए हमारा जो एंगल है वो लीडिंग रहेगा. In a pure or ideal single pole RC network, it would produce a maximum phase shift of exactly 90 degree. अगर हमारा pure capacitor है तो phase shift exact 90 degree हमारा होगा. And because 180 degree of phase shift is required for oscillation, at least two single poles network must be used within RC oscillator design. अब इसमें हम क्या करने वाले हैं, RC जो फेज शिफ्टर है वो हम कैसे बनाएंगे. तो हमने ये पहले एक आइडियल जो है फेज शिफ्टर डायग्राम बनाया. इसमें हमने एक कैपेसिटर और एक रेजिस्टर कनेक्ट किया हुआ है. तो कैपेसिटर लगाने से क्या होता है, पावर फैक्टर जो है वो लीडिंग होता है. तो इसमें हमारा लीड करेगा, अगर हमारा प्योर कैपेसिटर है तो 90 डिग्री लीड करेगा. तो अगर हमें 180 डिग्री शिफ्ट करना है तो ऐसे हमें दो नेटवर्क लगेंगे. यही हमने इसमें लिखा हुआ है. At least two single pole network must be used within RC oscillation design. तो हमें कम से कम दो नेटवर्क लगेंगे जो कि 90-90 ऐड करके 180 डिग्री शिफ्ट करें. However, in reality, it is difficult to obtain exactly 90 degree of phase shift for each RC stage. डिफ़िकल्ट क्यों है, क्योंकि हमारे पास प्योर कैपेसिटिव लोड नहीं होता, इसलिए हमारे पास जो एंगल है वो प्योर 90 डिग्री लीडिंग नहीं रहेगा, है ना. तो प्रैक्टिकली ऐसा पॉसिबल नहीं है. सो वी मस्ट देयरफॉर यूज मोर RC स्टेज कैस्केडेड टुगेदर टू ऑब्टेन द रिक्वायर्ड वैल्यू at the oscillation frequency. The amount of actual phase shift in the circuit depends upon the value of resistor R and the capacitor C. कितना phase shift होगा, इसके लिए हम resistor की और capacitor की proper value को select करेंगे. At the chosen frequency of oscillation with the phase angle phi being given as RC phase angle. So XC, we know that XC is equal to 1 upon omega C. ओमेगा की वैल्यू होती है 2 pi f. So XC is equal to 1 upon 2 pi f into C. and R is equal to R ही दिया हुआ है मुझे, and Z actually XC is called the capacitive reactance, XC जो है, R is called the resistance and Z called the impedance. So Z is equal to, we know that, under root R square plus XC square, and the angle phi is equal to tan inverse XC by R. तो इसके थ्रू हम फेज शिफ्ट एंगल निकाल सकते हैं अगर हमारे पास C और R की वैल्यू गिवन है। तो हम बता सकते हैं कि हमारा जो नेटवर्क है, पहला जो हमने ब्रांच लगाई है R और C की, वो कितना डिग्री फेज शिफ्ट करेगा, 60 डिग्री, 50 डिग्री, 80 डिग्री, वो हम इस फॉर्मूले के थ्रू आसानी से निकाल सकते हैं। Where XC is the capacitive reactance of the capacitor, R is the resistance of the resistor, and F is the frequency. In our simple example above, the value of R and C has been chosen so that at the required frequency, the output voltage leads the input voltage by the angle of about 60 degree. Then the phase angle between each successive RC section increase by another 60 degree. मतलब एक जो हमने RC सेक्शन बनाया हुआ है वो 60 डिग्री का फेज शिफ्ट कर रहा है। अगर हमें 180 डिग्री करना है तो हमें 60 का लगाएंगे, 60 प्लस 60 120 प्लस 60 तो 180 डिग्री। तो ऐसे में 3 नेटवर्क लगाने पड़ेंगे। Then the phase angle between each successive RC section increased by another 60, giving a phase difference between the input and output of 180 degree. 3 multiply 60 as shown by the following vector diagram. चलिए हम वेक्टर डायग्राम से भी देख लेते हैं। This is the vector diagram. तो अगर पहला वाला हमारा RC नेटवर्क हमने 0 पे लिया हुआ है, इसके बाद हमने RC प्लेस किया हुआ है पहला नेटवर्क, तो हमारा 60 डिग्री जो है वो शिफ्ट होगा। ऐसे ही हम दूसरा यहाँ पे RC नेटवर्क प्लेस करेंगे तो 60 प्लस 60 120 डिग्री हो जाएगा। ऐसे ही जब हम तीसरा RC नेटवर्क कैस्केडिंग में प्लेस करेंगे तो हमारा पूरा 180 डिग्री फेज शिफ्ट जो है वो हो जाएगा। थर्ड में हमारा कितना होगा, यहाँ पे 120, और फिर 120 में हम और 60 ऐड कर देंगे तो हमारा 180 टोटल हमें फेज शिफ्ट मिल जाएगा। So by cascading together 3 such RC network in series, we can produce a total phase shift in the circuit of 180 degree at the chosen frequency, and this forms the base of RC oscillators, otherwise known as phase shift oscillators, as the phase angle is shifted by the amount through each stage of the circuit. Then the phase shift occurs in the phase difference between the individual RC stage. Conventionally, operational amplifier circuits are available is quad IC package, for example LM124 on LM324, etc. So 4 RC stages could also be used to produce the required 180 degree of phase shift at a required oscillation frequency. We know that in amplifier circuit, either using a BJT or inverting operational amplifier configurations, it will produce a phase shift of 180 degree between its input and output. If a 3-stage RC phase shift network is connected as the feedback network between the output and input of amplifier circuit, then the total phase shift created to produce the required regenerative feedback is 3 multiply 60 plus 180 is equal to 360 degree or 0 degree as shown in a figure. The 3 RC stages are cascaded together to obtain the required slope for a stable oscillation frequency. The feedback loop phase shift is 180 when the phase shift of each stage is 60 degree. This occurs when omega is equal to 2pf is equal to 1.732 divided by RC, as tan 60 is equal to 1.732. Then, to achieve the required phase shift in RC oscillator circuit is to use multiple RC phase shifting networks such as the circuit below. Basic RC oscillator circuits. The basic RC oscillator, which is also known as the phase shift oscillator, produce a sine wave output signal using a regenerative feedback obtained from the resistor capacitor RC ladder network. This regenerative feedback from the RC network is due to the ability of the capacitor to store an electric charge. So this is the diagram of basic RC oscillator circuit. This resistor capacitor feedback network can be connected as so and above to produce a leading phase, means phase advanced network, or interchanging to produce a lagging phase shift. The outcome is still the same as the sine wave oscillation, only occur at the frequency at which the overall phase shift is 360 degree. तो इसको हम दो तरीके से यूज कर सकते हैं, लैगिंग के लिए भी और लीडिंग के लिए भी. By varying one or more of the resistors and capacitor in the phase shift network, the frequency can be varied, and generally this is done by keeping the resistance the same and using the three-ganged variable capacitor, because capacitive reactance XC change with the change in frequency, as the capacitors are frequency sensitive components. However, it may be required to readjust the voltage gain of the amplifier for the new frequencies. If the three resistors are equal in value, that is R1 is equal to R, R2 is equal to R3, and the capacitors C in phase shift network are also equal in value, C1 is equal to C2 is equal to C3, then the frequency of the oscillation produced by RC oscillator is simply given as Fr is equal to 1 upon 2 pi RC under root 2 into N, where Fr is the oscillator output frequency in Hertz, R is the feedback resistance in ohms, C is the feedback capacitance in farads, and is the number of RC feedback stages. This is the frequency at which the phase shift circuit oscillates. In our simple example above, the number of stages is given as 3. So n is equal to 3 is equal to under root 2 into 3 is equal to root 6. For the 4-stage RC network, n is equal to 4, so is equal to under root 2 into 4 is equal to root 8, etc. Since the resistor capacitor combination in RC oscillators ladder network also act as an attenuator, that is, the signal reduced by some amount as it passes through each positive or each passive stage. It could be assumed that three phase shift sections are independent of each other, but this is not the case, as the total accumulative feedback attenuation become minus 1 by 29th in bracket V0 minus V in or Vi is equal to beta is equal to minus 1 upon 29 across all the three stages. Thus, the voltage gain of the amplifier must be sufficiently high enough to overcome these passive RC losses clearly, then in order to produce a total loop gain of minus 1 in our three-stage RC network above, the amplifier gain must be equal to or greater than 29 to compensate for the attenuation of the RC network. The loading effect of the amplifier on the feedback network has effect on the frequency of oscillation and can cause oscillator frequency to be up to 25% higher than calculated. Then the feedback network should be driven from a high impedance output source and feed into the low impedance load such as a common emitter transistor amplifier, but better still is to use an operational amplifier as it is satisfy these conditions perfectly. So RC oscillator use an operational amplifier. When used in RC oscillator operational amplifier, RC oscillators are more common than their bipolar transistor counterparts. The oscillator circuit consists of negative gain operational amplifier and 3-section RC network that produce the 180-degree phase shift. The phase shift network is connected from the operational amplifier output back to its inverting input as so below. So this is the diagram operational amplifier phase lead RC oscillator circuit. तो इसमें जो डायग्राम है वो क्या करेगा, फेज लीड सर्किट डायग्राम या फेज को लीड करेगा. As the feedback is connected to the inverting input, the operational amplifier is therefore connected in its inverting amplifier configurations, which produce the required 180-degree phase shift, while the RC network produce the other 180-degree phase shift at required frequency. So 180 plus 180 equals 360 degree. This type of the feedback connection with the capacitors in series and the resistors connected grounded 0-volt potential is known as phase lead configurations. In other words, the output voltage lead the input voltage, reducing a positive phase angle. But we can also create the phase lag configuration by simply changing the position of RC components so that the resistors are connected in series and the capacitor are connected in grounded 0-volt potential as shown. This means that the output voltage lag the input voltage, producing a negative phase angle. Phase lag RC oscillator circuit. However, due to the reversal of the feedback components, the original equations of the frequency output of the phase lead RC oscillator is modified to Fr is equal to under root of 2n divided by 2 pi into RC. Although it is possible to cascade together only two single pole RC stages to provide the required 180 degree of phase shift, the stability of the oscillator at low frequency is generally poor. One of the most important features of the RC oscillator is its frequency stability, which is its ability to provide a constant frequency sine wave output under varying load condition. By cascading 3 or even 4 RC stages together, 4 multiply 45 degree, the stability of the oscillator can be greatly improved. RC oscillator with 4 stages are generally used because commonly available operational amplifier come in quad IC package. So, designing a 4-stage oscillators with 45 degree of phase shift relative to each other is relatively easy. RC oscillators are stable and provide a well-shaped sine wave output with the frequency being proportional to 1 upon RC, and therefore a wider frequency range is possible when using a variable capacitor. However, RC oscillators are restricted to frequency application because of their bandwidth limitation to provide the desired phase shift at high frequencies. Next is references. So these are the references. And thank you for watching this video.